Now that we've discussed putting electrons into simple atoms like hydrogen and helium, we need to think about what's going to happen when we add even more electrons. As soon as we start occupying the n equals 2 shell, every shell that we add electrons to is going to have more than one subshell. So when we have the n equals 2, we're going to have an s orbital, and we have one of those. And we'll also have p orbitals, and we have 3 p orbitals in the n equals 2 shell. Now, as the numbers of n go up, we can add in d orbitals and f orbitals, but we'll start simply with the n equals 2 and the s and the p. When we think about hydrogen, it only has one electron, and so all the orbitals in a shell are going to have the same energy. And that is because there are no other electrons having a repulsive force against any given electron. So when an atom only has one electron, all of those orbitals within a shell have the same energy, and those are known as degenerate orbitals. As soon as we start adding multiple electrons to an atom, the subshells within the shell don't all have the same energy. The orbitals all have different energy, and that's what's known as sublevel splitting. And we need to keep sublevel splitting in mind when we start adding electrons to larger atoms. Before we think about the consequences of sublevel splitting, let's think about where it's coming from. We can describe the energy between charged particles using Coulomb's law. And here's Coulomb's law here. This is an energy term. This is a constant. And then here we have Q1 and Q2, and that is the charge on each of 2 charged particles. And r is the radius, or the distance between those 2 charged particles. All right. So if we look at this, this is a constant. It's not going to change, so we don't need to worry about it much. If we want to think about the implications of this for energy, we have a few things that we can look at here. First of all, we can have Q1 and Q2 having the same charge, or we can have them have the opposite charge. So if we have Q1 and Q2 having the same charge, the energy for that is going to be positive, because there's no other term here that would cancel out that positive. A positive times a positive is positive. The energy is positive. And when we have a positive energy like that, the particles are going to repel. And we know that. We know that particles that have the same charge will repel each other. We can keep looking at this and understand that if Q1 and Q2 have opposite charges, the energy term, we're going to be multiplying a positive times a negative, so the energy is going to be negative. Okay? That means that these 2 particles coming into proximity are actually going to attract each other. Okay? And that's the case when we have an electron, which is one charge that's negatively charged, in proximity to a positive charge, such as the positive charge from a nucleus. In addition to just getting that qualitative view of whether the sign is going to be positive or negative, we can see that if we increase the magnitude of the charges, we're going to increase the attraction or repulsion. Okay. So if we have, for example, the charge of an electron doesn't change, but the charge of a nucleus can, because we don't always have the same number of protons in a nucleus. So for any given electron, the more protons there are in the nucleus, the greater the magnitude of that charge. And since protons and electrons attract each other, we're going to increase that attraction as the nucleus increases its charge. We can also see from this that our term here is divided by a distance term. And what that tells us is the greater the distance we have between particles, the lower the attraction is. And if the distance gets to be great enough, they don't actually interact at all. So the distance also matters in this. We care about magnitude and we care about distance. Now we need to think about a couple of ideas in terms of where the electrons are distributed and how that affects their interaction with the nucleus. So the first thing we're going to talk about is shielding. And in shielding, what's happening is the inner electrons are actually blocking the outer electrons from seeing some of the charge in the nucleus. So I'm going to pull up, this is, as we know, because we know the Bohr model isn't correct, effectively a Bohr model of the atom, but we're going to use it because it gives us the right idea, understanding that we're working with orbitals and not just circles of regions or shells outside of the nucleus. But let's start off with helium. So helium has an atomic number of 2. So we can put 2 positive charges here in the nucleus. And then we're going to call this the n equals 1 shell, and this is the n equals 2 shell. All right. So in helium, we have 2 electrons, and they're both in the n equals 1 shell. So they're going to be somewhere within this n equals 1 shell. As we add another proton and electron, so we're going to have lithium now. So we add a proton, and we're going to add an electron, and that one's going to go into the n equals 2. What's happening now is any electron is going to be attracted to the nucleus because we have these opposite charges. But this electron is also affected by these negatively charged particles here, which it's going to be repelled by. So what ends up happening is these negative charges block, effectively, some of the attraction for this electron to the nucleus. And so when we think about what the outer electrons are seeing of the nucleus, we have to think about an idea called effective nuclear charge. And what effective nuclear charge is going to be equal to is the atomic number, which is the number of protons in the nucleus. And this is an approximation, but it's going to work well enough for what we want to do, minus the number of inner electrons. Okay. So what that gives us in this case is we have a nuclear charge of 3, but there's 2 inner electrons. And so we have an effective nuclear charge of 1. This isn't completely exact, but like I said, for what we're trying to do, it works well enough. But the effect of this is that this electron's energy is higher. Not only is it farther away, but it also sees less of the nucleus because it's being blocked by these 2 electrons. Okay? So as effective nuclear charge decreases, the attraction to the nucleus decreases because, remember, the magnitude of the charges is important, and we drop the magnitude, and we're also going to drop that attraction to the nucleus. And the energy increases. And that might not sound right away because, of course, the magnitude of the energy, or the number, is actually going to drop. But what we're going from is a number that I'm going to make up an arbitrary number. Let's say it started off as minus 100. What we're going to do is we're going to get a number that's less. We're going to go to something like minus 50. So the magnitude, the absolute value of this number has dropped. But since this is exothermic and very energetically favorable, this is less energetically favorable. So the energy of that electron is increasing by that metric. Now that we've looked at shielding, we can understand why the different shells have different energy, because not only do we have a different distance from the nucleus, but we also have some interference of seeing the full charge of the nucleus by the inner electrons. But that does not yet explain why different orbitals in the same shell will have different energies. So let's take a look at another phenomenon, and that's called penetration. Now, I'm using this diagram because it's simple and easy to visualize things, but we have to remember that orbitals are not just electrons zipping around in a circle. Orbitals are probability distributions. So what they do is give us a sense of where it is likely to find an electron. And they all have different shapes, certainly, than this. The S's are spherical, but the P's and D's and F's get more complicated. When we have larger n values, so we increase the number for the shell, we have higher probabilities that are farther from the nucleus, but no matter what, every orbital we have has some probability of having an electron close to the nucleus. So we have this idea called penetration. And penetration is how probable it is to find the electron near the nucleus. So if we go back to our lithium atom with 3 protons and our 2 inner electrons, and it doesn't matter where I draw them, they just have to be in that shell. We could have an n equals 2 electron that is, in general, more likely than not, able to find a lot of... We could have an n equals 2 electron that is likely to spend a lot of time out here, but because it's a probability distribution, sometimes it'll be out here, and sometimes this n equals 2 electron will manage to get in here. And this time that's spent close to the nucleus is called penetration. When we have penetration, this electron is in a lower energy state because not only does it seeing the full magnitude of the charge of the nucleus, because it's not shielded in the same way by these inner electrons, it's also much closer, and the magnitude of that energy is going to be larger when it's closer. So penetration and shielding are important, but let's think about what that actually means for sublevel splitting. And so to do this, we're going to start and we're going to look at some radial distribution functions. And so that's what this is. And as we go out this axis, we're looking at the distance from the nucleus. And as we go up this axis, it's the total probability of finding an electron. And the shaded area here is the 1s. And as we know, it's a spherical orbital. And we have a high probability of finding the electron fairly close to the nucleus. So when we have sublevels in the same n value, or the same shell, they're going to have different radial distribution functions. It isn't the same for every type of orbital. And so the different RDFs are going to have different degrees of penetration. And let's take a look at this. This is the 2s orbital. And you can see right here it's got a node. A node is a region of 0 probability, which you learned about in Chapter 7. And this is the 2p orbital, or the 2p subshell, I should say, the 2p orbitals. So if we look at this, even though this has a peak that's a little bit closer to the nucleus than the 2s, what we have here is this region of penetration in the 2s. And so that has a fairly decent-sized region of greater penetration, and as a result of that, these two subshells have different energies. And the 2s actually has a lower energy because of that penetration than the 2p does. And so you can continue looking at these radial distribution functions for everything in the n equals 3 shell or the n equals 4, but what this ends up meaning is that any given shell level, the ns shell is going to be lower energy than the np, which is lower energy than the d, which is lower energy than the f. So our energy ordering is S is the lowest, then P, then D, of course if it's there, and again if it's there, F. So what does this mean for where electrons are placed? And we're going to introduce a couple more ideas here that we have to pay attention to when we're writing electron configurations. And the first is called the Aufbau principle, and that literally means building up. And what that tells us is when we're adding electrons to an atom, we're going to add them to the lowest energy orbitals first. So this, of course, is important. We just decided how to figure out what the lowest energy orbitals are, and now we know that we need to understand that in order to be able to place the electrons in the lowest energy orbitals. Another thing that we want to consider is Hund's rule. And what that tells us is when we're filling orbitals of the same energy, so this means all of the 2p orbitals, for example, or all of the 3p orbitals. We have several orbitals available of the same energy. We're going to fill them with 1 electron each before we add a second electron to any of them. And the reason we do that is because it's more stable. And really, when this is going to concern us is when we're drawing orbital diagrams, but there's other times that we need to understand that we're not going to have all of our electrons paired unless we have a completely full subshell. So, having considered all this, let's take a look at the ordering of sublevels with regard to energy. So in this, we have a listing of subshells. It's by no means complete because we can have subshells that are much higher than what we have listed, but it's sufficient to get the point across. So here, towards the bottom, we have low energy, and as we go up this, we're increasing in energy. And we can see that as we start off, the 1s is the lowest energy, so we're going to fill that first with electrons. And then coming up, the next energy is the 2s, and then the 2p. And just like we just discussed, the 2p is a slightly higher energy than the 2s because of that difference in penetration of the orbitals. Going up from there, next we're going to fill the 3s, and then the 3p. So we might start to think that the next thing we want to fill is the 3d because the shell is lower than 4, but if you look at the actual energies, they're close, but the 4s is actually lower in energy than the 3d. So after the 3p, we're going to go to the 4s and fill that before we go to the 3d. So what we're always filling in when we fill in d's is we will already fill the ns, so the 4s before the 3d. We'll do the 5s before we do the 4d. Okay? So we go from the 4s to the 3d and then to the 4p. So we've got the 4p, and we're going to go to the 5s. And one thing you can see is that these orbital energies are starting to get really close together. Okay, so in some cases we're going to have exceptions for how these are filled, but it's more important for you at this level to really understand the general order in which we're going to fill things. Memorizing exceptions isn't important at this stage. So we have the 5s, and then we're going to fill the 4d. Okay, and you'll notice we have a 4f here, but we're not ready to fill it yet, even though it's down in the 4s. Okay, so 5s, 4d, and then 5p. Then we're going to go to 6s. And this is where it gets really complicated because we're going to fill a little bit of the 5d, and then the 4f. Then we're going to finish filling the 5d, and this will make sense when we talk about how to do this from the periodic table before we move on to the 6p. Really, the most important things that you need to be aware of, though, are going through this much. So you should be aware that we're going from 1s to 2s and then through, and you should also be aware that we fill the 4s before we fill the 3d. But knowing the order of the orbitals this far is going to be important. And remember that the reason for the sublevel splitting is that the different subshells have different degrees of penetration in their RDFs. So next we'll start writing electron configurations with our understanding of what order these get filled.